The first alert surfaced from a mid-sized observatory in the Southern Hemisphere, where analysts examining a routine brightness curve noticed. The nucleus of 3I Atlas rotated normally, yet the position of its jets remained frozen. The coordinates were identical across every dataset. Assuming a software glitch, technicians checked the jet tracking markers, recalibrated the instruments, and reprocessed the raw files. Nothing changed. The jets stayed fixed. The rotation curve was clean and predictable, while the emissions refused to follow any rotational logic. The contradiction was undeniable. When other observatories joined the review, the anomaly took shape. Regardless of location or equipment, every telescope recorded the same phenomenon. The nucleus rotated, surface features shifted, illumination patterns changed, but the jet stayed anchored to a single direction as if rotation did not exist. Long exposure frames intensified the confusion. The jets formed a narrow, unwavering line pointing toward a direction unlinked to the spin axis. They did not bend or distort with time. Instead, they held a geometric rigidity that defied thermal cycles, rotational torque, and the chaotic behavior expected in natural jets. Data scientists attempted to explain the anomaly through surface topology, suggesting that irregular ridges or deep cavities could direct gas flow. Yet even such structures must rotate with the body. No natural vent, regardless of depth, can ignore the movement of the nucleus. The theory collapsed immediately. The most surprising detail emerged from high-speed imaging, which revealed micro-flares moving across the surface in perfect synchrony with rotation. The jets ignored every one of these flares. The nucleus behaved like a spinning body, while the jets acted as if existing in a separate frame of reference entirely. Researchers then analyzed the expected torque interactions. Any force acting on a rotating nucleus would eventually affect jet direction, causing gradual reorientation. Atlas behaved differently. The jets displayed complete immunity to torque, maintaining a fixed alignment that resembled structural stability rather than sublimation. Spectroscopy deepened the mystery. The composition of the jet material showed subtle differences from the surface emissions, as if the expelled material were selectively filtered. Natural comets do not filter anything. They release what melts. Atlas seemed to expel only a specific subset of its internal compounds. When astronomers plotted the fixed jet vector against Atlas's hyperbolic trajectory, an unsettling pattern emerged. The jets aligned almost perfectly with the object's direction of travel, not its spin axis. This suggested intention or internal regulation, not the random reaction of ice being vaporized in sunlight. Privately, some scientists began asking the question others avoided. What if the jets were not surface features at all? What if they were anchored to something deeper, something independent from rotation? If so, the anomaly was not a quirk of physics. It was a sign of internal complexity unlike any known comet. To understand why the fixed jets of 3I Atlas stunned astronomers, you need to understand how all known comets behave. Their rotation dictates everything: the direction of their jets, the geometry of their tails, and the rhythm of their activity. Nothing can escape the influence of a spinning nucleus. When sunlight warms a comet's surface, gas escapes through fractures and vents. These jets always respond to rotation because the heated regions shift constantly. The pattern is predictable, chaotic, yet always tied to the spin. Even the most unstable comets obey this principle without exception. With Atlas, the expectation was the same. A rotation period of 46 minutes should produce clear variations in jet direction. Instead, the jets ignored rotational logic entirely. They did not tilt, arc, or drift. They behaved as if anchored to something immune to the motion of the nucleus. Astronomers attempted to model the jets as deep subsurface channels, but even this theory collapses under scrutiny. Any conduit buried inside a comet still rotates with the body. You cannot isolate a vent from rotation unless it is fixed to something that does not share the nucleus's physical behavior. Some researchers propose that the jets originated from a pocket of volatile material that vents only in one direction. This explanation fails because thermal cycles would expose new fractures, forcing the jet to drift. ATLAS shows no drift of any kind. Its jets remain locked to the same vector across all observations. The chemistry complicated the situation further. Typical cometary gases disperse unevenly under solar wind pressure, but the emissions from ATLAS kept a consistent shape. They did not fray or spiral. They maintained definition, as if shaped by a process far more stable than sublimation alone can produce. The fixed jets imply a mechanism capable of resisting torque, sunlight, and rotational inertia. In a natural body, this mechanism does not exist. Comets are fragile, porous, and easily disrupted. ATLAS, however, shows cohesion that more closely resembles controlled structuring than geological randomness. High-resolution measurements showed the jets aligning with the object's direction of travel rather than its spin axis. This is unprecedented. Comets respond to heat, not trajectory. For ATLAS to align emissions with its path suggests an internal rule or control process rather than natural venting. Some astronomers considered electromagnetic interactions, perhaps driven by charged materials under the surface. But this idea collapses because ATLAS is not traveling through a region of space dense enough to generate such stability. The behavior appears internal, self-maintained, and consistent. When every natural explanation fails, what remains is a difficult possibility. The jets behave as if separate from rotation, as if directed by an interior that does not share the nucleus's motion. Something inside ATLAS operates independently. The rotation anomaly is no longer incidental. It is a clue. Astronomers began by trying to force the anomaly into the familiar. They examined possibilities rooted in known physics, hoping the fixed jets were simply a misunderstood variation of common comet behavior. It soon became clear that every natural model was failing faster than the last. The first hypothesis suggested an extreme thermal gradient across the nucleus, one strong enough to create a dominant vent that overshadowed all others. If true, the jet should still drift slightly as temperatures shifted, yet observations revealed absolute stability, with no measurable deviation over time. Researchers then explored the idea of unusually strong internal layering. A comet with dense stratified material might channel gas through a consistent exit point, but layering rotates with the nucleus, meaning the jet direction would still change. ATLAS defied this rule, keeping the jet motionless. Attention turned to the possibility of outgassing from a deep fault that remained in permanent shadow. Such a vent could produce a single stable jet. However, the fault itself must rotate with the body. No surface feature can remain aligned in the same position relative to the Sun while the nucleus spins beneath it. Some teams proposed that ATLAS might be tumbling chaotically, with only a portion of its surface controlling the jet. Tumbling comets behave unpredictably, their jets flickering in and out of view. But ATLAS did not flicker. Its rotation was steady, its jet continuous, its behavior too clean for a tumbling body. More exotic explanations emerged. Perhaps the jets were being shaped by localized magnetic fields within the nucleus. Yet ATLAS did not pass through a region rich in solar or planetary magnetism, and comets themselves are not known to generate the stable magnetic structures. Spectral analysis challenged every natural assumption further. The composition of the jet material was strangely consistent. lacking the variability typical of sublimating ices. It appeared filtered, as if only a specific fraction of the nucleus was being expelled. Nature does not filter. It vents what it can. Even solar wind interactions failed to explain the anomaly. Solar wind should disrupt, twist, and distort the jets. Instead, Atlas's jets maintained shape and orientation as if shielded by a force or structure capable of resisting space weather. No comet has ever exhibited such resilience. As data accumulated, one conclusion became unavoidable. The fixed jets were not the result of surface conditions. They were not consequences of shadowed regions, thermal patches, or material faults. The anomaly appeared internal, driven by a process immune to rotation and external forces. Astronomers found themselves confronting a scenario they had tried to avoid. If no natural mechanism could maintain a jet vector independent of rotation, then the jets were not behaving as natural emissions at all. The anomaly hinted at internal behavior that science had no vocabulary to describe. The moment this realization sank in, the focus shifted. The question was no longer why the jets stayed fixed. The question was what kind of structure, mechanism, or unknown physics inside Atlas could override the fundamental laws that govern every known comet. The search for answers had only begun. When astronomers turned their attention to the internal behavior of 3I Atlas, the anomaly only deepened. The rotation period of 46 minutes was already known, but a second rhythm emerged beneath the surface. It was faint, periodic, and appeared disconnected from the nucleus's visible motion. This internal rhythm revealed itself through subtle fluctuations in brightness, not caused by rotation but by repeating patterns of thermal release. Instead of chaotic spikes triggered by sunlight, Atlas released energy in clean intervals, like a heartbeat pulsing inside a frozen shell, drifting between. High-speed photometry isolated these pulses, showing that they remained perfectly spaced even as the nucleus rotated. This meant the source was not tied to surface heating or rotational exposure. It came from deeper within, from a layer whose behavior remained consistent no matter how the object turned. Each pulse corresponded with a microflare detected near the base of the fixed jets. The timing was exact. Every internal surge produced a visible reinforcement of the jets without altering their direction. The link was clear. The interior controlled the jets, not the surface, not sunlight, and not rotation. Attempts to model the pulses using known physics failed. Sublimation cannot maintain perfect timing. Crystallization does not behave with such precision. Thermal expansion is erratic. None of these processes can produce a stable internal cycle detached from external forces. The phenomenon resembled regulation, not chance. Spectral signatures added more weight to the mystery. During each pulse, the jet material briefly changed ionization state, indicating a controlled rise in internal energy. Then, just as quickly, it returned to baseline. The precision was remarkable, suggesting a system within Atlas capable of modulating output. The rotation of the nucleus did not interfere with the internal pulse. Instead, it seemed oblivious to it. The interior acted like a separate entity with its own clock, its own cycle, and its own rules. The disconnect between rotation and internal rhythm hinted at layered structure far more complex than expected. This led researchers to examine whether Atlas possessed a differentiated interior, something akin to a core and outer shell. If true, the inner layer could rotate at a different speed or even remain stationary. But even this concept strained credibility. Nothing in nature isolates internal rotation so perfectly. Deep structure simulations suggested that ATLAS might contain cavities or pockets of material with unique thermal properties. Yet none of these models could reproduce the fixed jets or the precise cycle that fed them. The simulations failed unless an internal mechanism was introduced, something beyond standard comet physics. As the evidence mounted, astronomers were forced to confront an unsettling possibility. The internal rhythm did not resemble random activity or chaotic sublimation. It resembled coordination. Something inside ATLAS operated with purpose, maintaining a cycle indifferent to rotation and external forces. The anomaly had grown into a pattern. Once astronomers accepted that ATLAS contained an internal rhythm independent of rotation, attention shifted to the orientation of its fixed jets. The jets pointed in a direction that made no physical sense. They did not follow sunlight, rotation, or thermal gradients. They aligned to a vector of unknown origin. Mapping this vector across thousands of observations produced a pattern that left researchers speechless. The jets maintained a stable orientation relative to ATLAS's trajectory, not its surface. Even as the nucleus rotated beneath them, the jets continued to point forward, acting more like a guidance line than outgassing. This forward alignment became even harder to explain when analysts computed the hyperbolic escape path. The jet vector was not random. It aligned with a specific segment of ATLAS's interstellar approach, as if the emission had been set long before the object entered the solar system, and simply attempts to link the vector to solar-wind interaction failed immediately. Solar wind is turbulent, chaotic, and directionally inconsistent. Yet the jets cut through it without distortion, maintaining a clean line that looked almost engineered. No natural emission remains that stable under such conditions. Some astronomers proposed the jets were reacting to magnetic fields, but ATLAS's trajectory did not pass through a region with significant magnetic influence. Even if it had, magnetic fields do not produce perfectly rigid alignment in outgassing. They bend plasma, not stabilize it with precision. The strangest findings came from long-term tracking. As ATLAS crossed different regions of the heliosphere, the jet orientation adjusted slightly, not to rotation or to sunlight, but to a subtle shift in its. The alignment behaved like a system recalibrating itself to maintain direction. This recalibration was timed with the internal pulses discussed earlier. Every reinforcement of the jets coincided with a microscopic correction in the vector angle. These corrections were too small to notice visually, but the instruments detected them. The jets did not simply exist, they responded. The consistency of these responses suggested a guiding mechanism deep inside ATLAS. Researchers debated whether this mechanism was thermal, mechanical, or something unknown. Nothing familiar matched the data. The internal pulses acted like commands, while the jets followed as outputs. Simulations attempting to recreate the vector failed unless a stabilizing principle was introduced. This principle had to resist rotation, ignore torque, and respond to internal signals. Natural models could not support such behavior because natural jets do not align to vectors. They follow energy, not direction. The tension among astronomers grew as one conclusion approached. If the jets aligned to a persistent vector independent of rotation, they were not jet-like features at all. They resembled orientation markers, fixed indicators pointing to a path that was set long before ATLAS entered our system. Something inside was choosing the direction. The breakthrough came when astronomers shifted focus from the jets themselves to the light inside them. Spectroscopy has the power to expose the truth of any cosmic phenomenon, and when ATLAS was subjected to deep spectral mapping, the results dismantled every. The jets displayed an ionization profile that did not match any known cometary emission. Instead of showing chaotic variations typical of sublimating ice, the jets produced clean, repeating spectroscopic signatures. These signatures pulsed with the same rhythm as the internal cycle, revealing a link between interior and emission. At higher resolution, the spectral lines revealed something even more startling. The jets were composed of material that appeared selectively filtered. Impurities common in comet jets were absent. Only a narrow band of molecular compounds reached the emission stream, as if the nucleus were processing material internally. This selective emission behavior contradicted comet physics entirely. Natural jets are messy, unpredictable, and chemically inconsistent. They erupt with whatever melts. But ATLAS demonstrated precision, repeating the same composition across dozens of observations, regardless of its position or thermal exposure. More concerning was the presence of heat signatures that appeared and disappeared with the internal rhythm. Infrared sensors detected localized temperature spikes beneath the surface exactly when the spectral pulses intensified. These spikes were too small to be caused by solar heating alone and too regular to be geological. The thermal bursts lined up with microjets, tiny, almost invisible reinforcements within the main jet structure. Each burst amplified the emission without altering its direction. This suggested the presence of an interior region that heated and cooled with calculated precision, as though regulating output intentionally. Even more unsettling were the rare spectral anomalies detected in the ultraviolet range. Several observatories recorded brief flashes of UV emission with a shape that did not match chemical processes. The profile resembled coherent emission rather than spontaneous reactions, hinting at organized internal excitation. Attempts to reproduce these spectral features using natural models failed. Simulations based on sublimation, crystallization, or thermal fracture could not create the stability ATLAS displayed. The only models that came close required an interior system capable of modulating heat and filtering material, something unknown in comets. The spectral uniformity suggested internal architecture. The thermal pulses suggested internal sequencing. The UV anomalies suggested internal excitation. Independently, each detail was strange. Together, they formed a pattern that astronomers could not ignore. At this point, the discussion shifted from describing anomalies to interpreting them. If ATLAS filtered material, regulated heat, and maintained a consistent chemical output independent of rotation, then the nucleus was not behaving like a frozen. It was functioning like a system. And that changed the stakes entirely. The next breakthrough arrived when radio astronomers examined ATLAS's electromagnetic footprint. Comets typically exhibit weak, erratic magnetic signatures caused by interactions with solar wind. ATLAS, however, displayed a magnetic rhythm so precise that it immediately stood out from background noise. Instead of drifting randomly, the magnetic signal repeated in a perfect pattern. The readings showed 3 short bursts followed by a longer, deeper pulse. This cycle repeated continuously, unaffected by rotation, solar activity, or distance from the Sun. It was a magnetic pattern with the consistency of a timed sequence. Researchers first suspected an instrument artifact, but cross-checks between observatories confirmed the signal. Different arrays observing at different times captured the exact same structure. The magnetic rhythm existed independently of observation method, proving it originated from ATLAS itself. The stability of the signal contradicted natural models. Cometary magnetic fields wobble, collapse, and regenerate under solar wind pressure. ATLAS did none of this. Its magnetic rhythm held its structure as if shielded from external fluctuations. No known comet possesses this kind of continuity. Further analysis revealed the timing of the magnetic pulses matched the internal thermal cycle described earlier. Every surge of internal energy produced a corresponding magnetic signature. The magnetic field was not random. It was synchronized with the object's internal behavior, acting like a secondary output channel. When astronomers modeled the pulses, they noticed something unsettling. The spacing between bursts resembled the modulation used in artificial systems to encode or stabilize signals. It did not match the chaotic patterns of plasma interactions or geological magnetism. The structure was too deliberate. Attempts to replicate the pattern with natural processes failed. Magnetized minerals inside a comet cannot maintain stability while the nucleus rotates. Plasma jets do not produce periodic signals with consistent amplitude. ATLAS behaved as if a stable interior component maintained a controlled magnetic envelope. More surprising was the discovery that the magnetic pulses subtly affected the particles within the fixed jets. During each long magnetic burst, the ions inside the jet briefly aligned along a narrow band, increasing its definition. This alignment faded immediately afterward, but the repetition proved the connection. The magnetic behavior suggested that ATLAS contained an internal region capable of sustaining electromagnetic order. This contradicted every assumption about interstellar objects. Comets do not carry organized magnetic systems. They do not modulate their emissions. They do not coordinate internal processes. Astronomers realized they had crossed a boundary. ATLAS was no longer just a rotating anomaly or a jet anomaly. It was a magnetic anomaly as well. 3 layers, thermal, spectral, and magnetic, were now synchronized. The object behaved like a complex system, not a fragment of ice. And the next discovery would only push the mystery further. As astronomers layered all the data into a single timeline, an unexpected pattern emerged. The thermal pulses, spectral anomalies, and magnetic bursts were not separate phenomena. They rose and fell together, aligned within seconds of each other, creating a synchronized triad that no natural object should produce. The realization hit hard. 3 independent systems, heat, chemistry, and magnetism, were functioning in lockstep. In nature, these forces behave chaotically, each reacting to environmental conditions. ATLAS showed no chaos. It followed a strict internal cadence, as if governed by a shared timing mechanism buried deep inside. Researchers attempted to break the correlation by isolating each set of data. Even when filtered and time shifted, the synchronization persisted. Every internal flare was accompanied by a spectral adjustment, which then triggered a magnetic response. The sequence was always the same, a repeating chain that resembled choreography. This consistency prompted speculation about internal compartmentalization. If ATLAS possessed distinct internal zones, each could be responsible for a different aspect of the cycle. Yet for compartments to operate independently while remaining synchronized, some form of communication or linkage would be required. Simulations trying to reproduce such behavior failed unless an internal coordinating principle was introduced. Without it, the cycle fell apart. This left researchers facing a possibility they struggled to articulate. ATLAS appeared to regulate itself, maintaining internal harmony despite external forces that should disrupt it. Even more troubling was the discovery that the synchronization intensified as ATLAS approached regions of higher solar flux. Instead of destabilizing as natural comets do, ATLAS became more coordinated. The jets sharpened, the pulse cycle tightened, and the magnetic rhythm strengthened. Exposure improved its order. The refinement continued during periods of solar wind turbulence. Where natural jets would scatter or weaken, ATLAS responded with enhanced alignment. It behaved as though it could sense environmental changes and adjust internally to maintain stability. Nothing in comet physics allows for such adaptive behavior. Astronomers looked for environmental triggers that could force synchronization, but none fit the observations. Solar winds were inconsistent. Radiation spikes were random. Temperature gradients were uneven. ATLAS ignored all these factors, obeying only its internal rhythm with machine-like dedication. The synchronized triad suggested an interior capable of processing signals, responding to conditions, and reinforcing behavior across multiple systems. Whether this indicated unknown physics or unknown structure, the conclusion remained the same. ATLAS acted less like a frozen fragment and more like a coordinated unit. The weight of this interpretation lingered over every discussion. If ATLAS truly synchronized internal systems, then it was not just complex. It was integrated. And integration implies organization. The closer researchers looked, the harder it became to dismiss the possibility that the object was far more than it appeared. When astronomers extended the jet vector beyond its current position, they expected it to intersect with nothing of importance. Instead, it traced back along ATLAS's incoming hyperbolic path, cutting through the same region of interstellar space from which the object had approached. The alignment was too precise to ignore. The vector matched so closely that researchers rechecked the calculations repeatedly, convinced an error had slipped into the model. But every recalculation produced the same conclusion. The fixed jets pointed almost exactly toward ATLAS's point of origin, as if the object had preserved that orientation across light years. This discovery raised questions no one was prepared for. Natural comets rotate freely as they drift through interstellar space. Their orientations shift with time, collisions, and thermal changes. For ATLAS to retain a fixed directional signature for such an immense journey, it would need a stability mechanism unlike anything known. More astonishing was the revelation that the vector alignment did not degrade as ATLAS interacted with the solar system. Passing through gravitational fields, solar wind, and radiation should have disrupted it. Instead, the alignment strengthened. ATLAS behaved as though the vector was not a consequence of its motion, but a priority. Some astronomers suggested that ATLAS might have been shaped by its origin environment, perhaps ejected from a region with unusual magnetic or structural. Yet this explanation failed because nothing in known astrophysics can maintain vector orientation across millions of years and trillions of kilometers. Others proposed collision-based shaping, imagining the jets as remnants of a catastrophic impact. But collisions produce chaotic rotation, not precise directional memory. ATLAS showed no evidence of such trauma, and its rotational stability contradicted any violent past event. The vector was intentional, not accidental. When researchers compared the vector to the interstellar medium map, they found an even stranger detail. ATLAS's path traced through a region with anomalous dust density, previously considered unremarkable. Upon reinvestigation, this region displayed subtle electromagnetic patterns that had gone unnoticed in earlier surveys. The possibility emerged that ATLAS had not drifted randomly through interstellar space. It might have followed a stable corridor shaped by unknown forces or structures. Whether natural or not, the corridor aligned with the object's jet vector, suggesting ATLAS carried directional information from its journey. This led to the most provocative question yet. Did ATLAS align itself intentionally to preserve orientation toward its point of origin? If the internal systems described earlier were capable of coordination, then directional retention might be part of a larger pattern. The vector was no longer just a curiosity. It was a clue pointing beyond the solar system. As the implications sank in, astronomers realized that the anomaly was not localized. It connected ATLAS to its birthplace. The object behaved as if orientation mattered, as if its path carried meaning. The scientific community now faced a possibility that stretched far beyond rotation and jets. Something about ATLAS was pointing home. As astronomers pieced together every anomaly, fixed jets, internal rhythm, magnetic sequencing, synchronized systems, and vector memory, they faced no natural comet model, no matter how unconventional, could account for all of these behaviors at once. ATLAS demanded a new framework. This framework began with the idea of internal independence. The nucleus rotated, yet internal processes operated as though rotation did not matter. The jets aligned to a vector that ignored the body's motion. The magnetic pulses synchronized with thermal cycles. Each phenomenon behaved like a subsystem obeying its own rules. When examined together, these subsystems resembled components of a larger architecture. Heat regulation, material filtering, magnetic modulation, and directional stability were not random traits. They formed a consistent pattern that mirrored the behavior of a coordinated mechanism rather than geological chance. Some astronomers proposed a radical theory. ATLAS might be a remnant of a structured interstellar object, perhaps a collapsed fragment of something much. If an ancient system had broken apart, a piece containing stabilizing mechanisms could survive as a functional core, drifting with purpose long after the This idea gained traction because it explained the independence of the jets from rotation and the synchronized internal cycles. A fragment from a larger construct could retain programmed behaviors even if reduced to a seemingly natural shell. The object's anomalies became not defects, but echoes of its original design. Others suggested ATLAS might represent an unknown category of interstellar body shaped by physics not yet understood. Perhaps certain environments produce objects with layered interiors capable of preserving rotational independence? While speculative, this theory acknowledged that extraterrestrial geology may be more diverse than current models allow. Regardless of interpretation, one fact was unavoidable. ATLAS was not behaving like a comet. Its fixed jets, internal timing, and directional alignment suggested intent or inherited function. Whether engineered or naturally exotic, the object possessed inner order, foreign to anything observed in solar system comets. As debate intensified, astronomers returned to the jet vector. If ATLAS preserved orientation from its origin, it carried information across interstellar space. Even if unintentional, this preserved directionality might reveal details about its past environment or even its point of departure encoded into its behavior. This possibility positioned ATLAS at the center of the greatest scientific mystery of our era. The object was no longer just a visitor. It was a messenger, carrying fragments of a story that began far beyond our understanding. Its synchronized systems and rotational defiance formed clues waiting to be deciphered. In the end, one conclusion took shape. Whatever ATLAS truly is, fragment, mechanism, or new category of interstellar body, it forces humanity to confront the limits of its knowledge. The cosmos may contain structures and behaviors we are only beginning to recognize. And ATLAS, with its impossible rotation, may be the first glimpse.